problem now. We have a point charge with a magnitude of 1 microcoulomb. So Q equals 1 microcoulomb. And it's in the cavity of an uncharged conducting shell with inner and outer radii. A equals 0.125 meters and B equals 0.175 meters. The first thing we're asked to find is what are the induced charges on the inner and outer surface of the shell. So we know that our positive point charge in the middle induces negative charge. It attracts negative charge to the inner surface. We can call that Qi. And it repels positive charge, so they go away to the outer surface. Call that QO. So following along what we did in the lectures, we found that the charge induced on the inner surface is equal and opposite of the charge that's in the cavity. It's minus Q or minus 1 microcoulomb. The charge on the outer surface has to be equal and opposite of what's on the inner surface because the total charge on the shell is equal to 0 because it's uncharged. If the shell had a charge, it would be a different story, and we will get to that example. So Q on the outer surface is minus of what's on the inner surface, so it's minus of minus 1 microcoulomb equals plus 1 microcoulomb. Okay, so that's that part done. Next, we'd like to find the electric field at some different distances. So let's first deal with using Gauss's law with spherical symmetry. So our Gaussian surface is a sphere with radius r. We know that Gauss's law says that the net electric flux is the integral of E dot dA equals Q enclosed over epsilon naught. Let's deal with the integral part. The integral of E dot dA is the integral of E times dA times the cosine of the angle between electric field and area. Since our sphere is our Gaussian surface, we know that the area vector points straight out. We know that our electric field vectors point straight out. Those two vectors are parallel, so we've got times the cosine of 0. So we've got the integral of E times dA. If we're a constant distance away, then we have a constant electric field. So we've got E times the integral of dA. Integral of dA is A. A is the area of the Gaussian surface or the sphere, so that's 4 pi r squared. Okay, if we put this together with our Gauss's law, we get E times 4 pi r squared equals Q enclosed over epsilon naught. And this gives us the form that we're going to use to calculate our electric field. E is 1 over 4 pi epsilon naught times Q enclosed over r squared. So we'll use this form. We've shown it's true for everywhere that we have the spherical symmetry. Our next bit will be to figure out the charge enclosed at each of these distances. The electric field at r equals 0.1 meters. Let's draw our Gaussian surface. We already established that we were going to use a sphere. So we need to draw a sphere with a radius of 0.1 meters. Remember, the inner surface is A, the outer surface is B. So for r equals 0.100 meters, our electric field is 1 over 4 pi epsilon naught times Q enclosed over r squared. The r part's not too hard because r is equal to 0.1 meters, epsilon naught is a constant, that part's okay. Q enclosed is the tricky bit. So we have to look at our picture and we ask, and I borrowed here our picture from what we did in lectures that had the picture of the electric field drawn on it. How much charge is inside the Gaussian surface that I just drew? Well, let's look at what's inside. None of the conductor is inside, so none of that charge could possibly count. We do have the point charge inside, so the only charge enclosed by our Gaussian surface is our point charge. The point charge. So Q enclosed equals Q equals 1 times 10 to the minus 6 coulombs. So we'll put that in for Q, we'll put in 0.1 for R, we'll put in our value for epsilon naught, and what we'll get for our electric field is 8.99 times 10 to the 5 newtons per coulomb, and the direction of that electric field is outward. Okay, that's the first part. Next we'll do at 0.15. Okay, for R equals 0.150 meters, well, what we know about that is the inner radius of my conductor A is equal to 0.125 meters. The outer radius of my conductor B is 0.175 meters. 0.15 meters is right smack in the middle of that conductor. So it's in the conductor. So there's two ways to do your answer here. You can, right off the top of your head, say E equals 0 because it's in a conductor in electrostatic equilibrium. Or you could go through the process of using your Gauss's law. If you used Gauss's law, your Q enclosed would be the charge on the inner surface of the conductor plus the point charge, and that would give us a net charge of 0. So that would be an okay strategy, but it's also okay just to say that the electric field is 0 inside of a conductor. Okay, last we'd like to find the electric field at R equals 0.2 meters. Let's draw our Gaussian surface. So that's going to be a sphere with a radius of 0.2 meters. It's going to be completely outside the conductor. We'd like to use our Gauss's law. The important part to know is what is Q enclosed. Q enclosed is whatever charge is on the conductor plus the point charge. The charge on the conductor is 0. And the point charge is 1 microcoulomb. So our electric field is equal to 1 over 4 pi epsilon naught times our charge enclosed, 1 times 10 to the minus 6 coulombs, divided by r squared, 0.200 meters squared. That gives us, for an electric field, 2.25 times 10 to the 5 newtons per coulomb, and the direction is out.